Welcome and thank you for standing by. At this time, all participants are in a listen-only mode. During the discussion, there will be question and answer sessions. To ask a question, please press star and then 1. This call is being recorded. If you have any objections, you may disconnect at this point. Now we'll turn the meeting over to your host, Sarah Fraser. You may begin.
Hi, everyone. Welcome, and thank you for joining us for today's Media Telecon. I'm Sarah Fraser with NASA's Office of Communications. In the next few weeks, a new NASA technology demonstration will launch to space as a payload aboard the Department of Defense's Space Test Program 3 mission. The Laser Communications Relay Demonstration, or LCRD, will be our first end-to-end laser relay system. It will send and receive data between space and Earth using invisible infrared lasers at a rate of 1.2 gigabits per second. Laser communication systems like this can provide data rates 10 to 100 times faster than traditional radio frequency systems, so they'll provide future missions with extraordinary data capabilities. Here to talk more about the benefits of this technology, the demonstration objectives, and deep space systems in development are Trudy Cordes, Director of Technology Demonstrations for NASA's Space Technology Mission Directorate, Badri Younes, Deputy Associate Administrator for NASA's Space Communications and Navigation Program, Dave Israel, LCRD Principal Investigator at NASA's Goddard Space Flight Center, and Miriam Wennersten, LCRD's Ground Segment Manager, also from NASA Goddard. We'll start with opening comments from these speakers and then open it up for questions. We also have someone else on the line to answer questions, A.B. Biswas, the Deep Space Optical Communications Technologist and Group Supervisor of the Optical Communications Group at NASA's Jet Propulsion Laboratory in Southern California. All right, and when we start that Q&A session, to get into the question queue, just a reminder, press star 1 on your phone. So first, we'll hear from our speakers, and I will first pass it off to Trudy Cordes.
Okay, thank you, Sarah. Good afternoon, everyone, and thank you for joining us today. On behalf of NASA's Space Technology Mission Directorate's Technology Demonstrations Program, as well as our partners in the Space Communication and Navigation Program, I think it's safe to say that we're all very excited about the upcoming launch of the Laser Communications Relay Demonstration payload. We've been working on this technology project for a while now, and we are more than ready to see this capability go to its demonstration phase. The objective of this demonstration is to prove out NASA's first bidirectional end-to-end test of a communication system that can transmit data at a rate of 10 to 100 times faster than our current radio frequency baseline systems. And with an optical downlink to transmit data back to us using lasers, this truly is a first of its kind demonstration. As one of the 5 main pillars of NASA, STMD's focus is on the importance of continued investments which provide significant benefit to our nation's society and economy. STMD's mission is to drive innovation and advanced technology, opening up greater opportunities for partnerships with industry, academia, and small businesses. Technology demonstrations and development by nature is a lengthy process that progresses through multiple stages. And because of the iterative process, it sometimes takes us a while to get to a point where NASA can take what I would call a smart risk to fly and demonstrate new technologies. It goes through idea inception, initial formulation, design, development, and testing, which can be iterative phases in and of themselves, and then demonstration of system-level technologies in the environment in which they're expected to operate. And ultimately, the goal is infusion of these new systems into future missions. So back to LCRD specifically. As missions generate and collect more data, higher bandwidth is needed to relay data back to us, and that's exactly what LCRD is testing and demonstrating. This new system will not only provide higher data transmission rates, but optimize what we call SWAP, or size, weight, and power. It'll be smaller in volume, weigh less, and use less power than current state-of-the-art. And as we work to establish a robust presence on the moon and ultimately send humans to Mars, tech demos like LCRD are absolutely critical to enabling our future mission needs. So LCRD does involve multiple partner organizations. The teams have done just an absolutely incredible job working together, especially adapting to pandemic protocols for integration and the launch preparation activities that are going on now. And I'd just like to mention the teams here. The LCRD project itself is led by NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's supported by the Jet Propulsion Laboratory in Southern California. Our partners have included MIT Lincoln Labs, which they've been absolutely instrumental in our technology development phase. Northrop Grumman built the spacecraft. And then the LCRD payload will ride along on the Department of Defense's STP-SAT-6. That is the satellite that it is integrated with, and it's part of the STP-3 mission, as Sarah mentioned at the opening. And it's operated by the U.S. Space Force's Space Systems Command. The launch will be on a United Launch Alliance, or ULA Atlas V, from Cape Canaveral Space Force Station in Florida. And launch is now set for December 4th. With the window opening at approximately 4 a.m. that day. So we will not only need a large supply of rocket fuel, but coffee as well for the humans. Yesterday, the U.S. Space Force held their flight readiness review, and they did declare a go for launch yesterday. So finally, once on orbit, LCRD operations are slated to begin in the spring of next year, and at that time, we'll start various experiments that are experiments from NASA, other government agencies, industry, and academia. And Dave Israel, one of our panelists, will talk more about this in a few minutes. LCRD is designed to operate for a minimum of 2 years, but we are hoping to get as many as 8 years of operation out of the payload. And the final thing I'd like to mention is that while LCRD will test laser communications from geosynchronous orbit, NASA has another advanced communications project in its final preparation stages and nearing launch readiness as well, and that's an optical communication system that will operate much farther out in deep space. So the very aptly named Deep Space Optical Communications Project, led by JPL, is set to launch in the summer of 2022 on NASA's Psyche mission, which is a mission to a metal asteroid, and that's being done by our colleagues in the Science Mission Directorate. DSOC will test laser communications against the distinctive challenges presented by deep space exploration, such as extreme distance pointing. So it's a busy and exciting time for us as we demonstrate multiple advanced communication systems and as well as other capabilities that we're currently working on in the Technology Demonstration Missions program. So just in closing, before I hand it over to our other panelists, in STMD we like to say technology drives exploration, and we say it often because we absolutely believe it. Whenever we launch a TDM project, I personally believe we're enabling the agency and nation and getting closer to our future mission plans. So thank you for the time today, and back to you, Sarah.
Thank you, Trudy. So next we'll hear from Badri about space communications and the benefits of optical communications. Badri?
Thank you, Sarah, and Trudy, thank you for all of the nice words you said. It's always great to have the kind of partnership that will advance technology and NASA's capability. They provide a lot of benefits, not only to NASA, but to the larger community of interest, to include the country and enabling economic growth as we commercialize the technology and make it available to our industry. But optical communications by itself is so critical to the evolution of NASA space communication navigation capabilities. I don't know whether any of you have heard, but we have designated this decade to be the decade of light, where we will be demonstrating the technology, optical technology. We expect to gain some experience with it before we infuse it into operation. The technology is so critical in so many ways. It provides a large bandwidth needed to meet not just NASA's appetite, but even the commercial sector's appetite for more and more bandwidths. So this is the kind of thing that will allow you to have much larger bandwidth than presently available. Second, it reduces the pressure on the RF spectrum. And there is plenty of contention for frequencies and for allocation between the private sector, different services in the private sector, as well as government agencies. So having that spectrum available to us, huge bandwidth, it would reduce the pressure and the contention on the lower frequency bands. Third, and Trudy mentioned that about the swap value. So this technology definitely it reduces the burden on the end user. The end user can benefit from this swap value, estimated to be about 2 order magnitude in terms of performance and better performance. Fourth, it enables better interoperability between different communities, in particular between different government systems, between government and commercial systems, because we won't be burdened by regulations. The optical frequencies are presently not regulated. And so, neither the ITU or the FCC or NTIA will try to put any burdens or any showstoppers for that different community can share the same optical band and be able to talk to each other and communicate among each other, provided they have similar waveforms. And so, this is something very critical, and I will be getting back to it. Interoperability is so critical to SCAN and to NASA. And five, and last but not least, the development of space-based optical networks will allow us to transition to quantum networking from space. We envision that to happen in 2030. So the optical communication is a stepping stone toward a much more capable, more robust technology that will come with so many promises in the future. We envision that to be in the 2030s. Going back to the issue of interoperability, as many of you have heard, NASA has decided to commercialize much of its near-Earth communication capability, acquiring communication services from the private sector. And we are pursuing an environment where our users can roam in space and can get support from any provider that's out there. However, the utilization of the frequency spectrum is burdened by heavy regulations. Each provider is operating at a certain frequency, at different frequencies. They all use different waveforms. The access to the spectrum is so heavily burdened by regulation, but not the optical domain. The optical domain will provide a common channel for all to communicate and be able to provide support for each other. This is so critical for us. That's why we are going to push this technology as far as we can. But first, we have to gain that experience with it, and because we are pursuing maximum flexibility for our users. So the technology we seek is something that will allow the user to roam in space, and transmit down to the ground or transmit, through space. Ultimately, not only NASA users will benefit, but also the industry at large will benefit from it. And I will be open to any question later on. Thank you.
Thank you, Badri. I am now going to pass it to LCRD's lead, Dave Israel.
Okay, hello. So the LCRD, the Laser Communications Relay Demonstration, consists of the flight payload, which is on board the SDP-SAT spacecraft that will soon be launched, SDP-SAT-6, spacecraft that will soon be launched, and it will arrive and function at a geosynchronous orbit location. And the relay part is that there are 2 optical terminals on board. So and each terminal is capable of a bidirectional optical communications link. And on board, between those 2 terminals is a switching capability that will allow us to receive data on one terminal, switch it over to the other terminal, and then relay the data to its destination. So when we first launched, then the 2 endpoints that LCRD's payload will be communicating with are 2 ground stations. One is in Haleakala, Hawaii, and the other is in Table Mountain, California. Those are our 2 optical ground stations, and our demonstrations will be really relaying data between these 2 ground endpoints. However, the terminal is designed to be able to track low Earth orbiting users. So in the future, next year, there'll be a terminal that we call Illuma-T that will be flying on the International Space Station that will give us that LEO user. So we'll be able to pick up a user with 1 terminal and then real-time relay from optical to optical link back with Earth. So this is different from the other activities that you hear a lot about now in the commercial world of laser communications and some other things that are flying that are more on the space-to-space link. And an important aspect that we're demonstrating is this space-to-ground optical link. So the challenges with optical back to the ground is that the Earth's atmosphere and the clouds are things that there's a certain point that we can't turn up the power and get past the bad weather like you can on an RF link. You have to steer your laser beam someplace else. So we need to get a lot of operational experience before we're able to use optical communications for our missions. And though we're out at the geolocation, of course, being at geo, we're above all the Earth's atmosphere and weather. So everything that we learned regarding that will directly be translated to supporting trunk lines from the moon or high data rates and trunk lines from the Mars or wherever else we want to go. So there are all those experiments that are based on our operations concepts dealing with the moon and dealing with the weather and the clouds. But then a lot of what we'll also be demonstrating is how do you use operational links. How do you make optical links an operational capability to support different scenarios? So we have the ability to simulate different user types and their data streams and flow it through our system so that we can demonstrate not just the optical technology, but put it in context of a larger network, be that a lunar relay or other systems. So this is really that operational demonstration. There was the lunar laser communications demonstration that flew on LADI in 2013 that was very successful, but we were only able to get a certain number of hours of time on that mission by design. So the 2 years on orbit will give us a lot of time to do a wide variety of experiments and gather a lot of data and refine our models. And then finally, I just want to mention that there is a guest experimenter program. So during the course of the experiments, we will be able to accommodate experiments where we can work with the interested experimenter to design an experiment that we can then use our terminal and ground stations to support various objectives that they might have. And that's it. Thank you.
Thanks, Dave. So now we'll hear from Miriam Wennerston about the ground station component of the LCRD demonstration. So Miriam?
Yes. Good afternoon, everybody. As Dave was talking about, one of the goals of LCRD is to help us learn how to run an optical network, and the ground segment is a major part of that network. And to reiterate what Dave said, we have 2 optical ground stations, which helps give flexibility to LCRD as a system. Our 2 ground stations are on mountaintops. OGS-1 is at Table Mountain, California, and OGS-2 at Haleakala, Hawaii. Why mountaintops? As Dave said, optical communication wavelengths can't penetrate clouds and are affected by the atmosphere. So placing optical ground stations on mountaintops gives the least atmospheric interference. And by placing the 2 ground stations geographically far away from each other, we have a better chance of having good weather at one if the other has clouds or rain. And as part of the LCRD experiment, we are collecting weather data at the ground station for analysis of the laser communications under the different conditions. We also, as part of the overall LCRD ground segment, we have our Mission Operations Center at White Sands, New Mexico, the LCRD MOC, or LMOC as we refer to it. The LMOC performs the overall state of health monitoring of the LCRD payload and also issues any commands to it. The LMOC also receives the telemetry that is generated by the ground stations themselves. For example, the telemetry from the optical modems that are on the ground. And we will be archiving and performing analysis on all of the data that's collected on the ground side as well as the flight side. The LMOC is basically the central brain of LCRD as a system, and I like to refer to it as sort of the orchestra conductor for all LCRD communications events. From the LMOC, we schedule the events against the available resources, possibly adapting the events based upon weather at one of the ground stations. For each optical event setup, the LMOC sends configuration commands to the LCRD payload for the correct laser pointing of which ground station to point to for this event, the correct link modulation, and also the data routing through the payload, as Dave had alluded to earlier. The LCRD payload can take data originating at one ground station and relay it to the other. And so after the LMOC configures the LCRD payload, it also then sends each ground station involved in the event its configuration information to set up the ground station to match the optical, to match what the configuration is on the optical terminal on the payload. While the events are ongoing, the LMOC monitors in real time the entire system and watches the links and data services that are riding on that link. You can think of the link as your connection at home to your neighborhood ISP, and the services is something like, streaming your favorite TV show. After those events, we'll have all of the telemetry archived and available to our experiment team for post-processing and correlation. So thank you very much.
Thank you, Miriam. So with our last speaker, we're now ready for questions. So just a reminder, if you want to get into the question queue, please press *1 on your phone. And when you're asking a question, please state your name, affiliation, and who your question is for. And as a reminder, we also have A.B. Biswas, the supervisor of the Optical Communications Group at NASA JPL, on the line to answer questions too. And so with that, I will take our first question from Elizabeth Howell.
Hi there. Thanks so much for taking the time. So I was curious. I know that the initial target date, or at least the firmer date, was supposed to be back in 2019, and there were obviously some changes that were sort of going on in that process and some reports. Can you talk a little bit about some of the changes that you might have made on your end, as well as adjustments to the payload, the testing, anything else that was sort of going on during that time, just to give me a little bit of context as to what was going on?
I will have Trudy start that answer.
Right. So you're right. LCRD was supposed to launch a couple of years ago. It was originally on a commercial provider, and there were issues with that. We had to change launch providers, and that changed some of the interfaces and integration requirements. So because it changed requirements, and we transitioned to the U.S. Space Force's space test program, it caused a launch shift because we needed to change payload accommodation design, which also affected our testing activities. And we've since, made those changes and have demonstrated the payload and space vehicle accommodations in the ground testing portion to now get to the launch date in December.
And also not to forget the effect of COVID-19 and the access that our people had to the payload, as well as all of the other entities involved in the integration of that payload on the spacecraft. So all of these things combined to cause a delay, not a single factor caused that.
Thank you.
All right, next we'll go to Devin Coldway.
Hey, thanks for taking the time to chat. Really quickly, obviously a relay like this would be very helpful for Artemis missions, anything going to cislunar space. Is that within the scope of this project, and how far out do you go until you start getting into the deep space laser relays like that other mission that was mentioned?
I will toss to Dave to answer that one.
Sure, thank you. So to answer this, I guess the second part first, right? So when you get farther out with the missions, then there's certain aspects that are there's two main points that come up. One is a loss of kind of signal power. We call it like a photon-starved environment. So the type of modulation that you use becomes different. So our LCRD mission has the capability to demonstrate both this pulse position type modulation that's useful for that photon-starved environment, as well as the modulation that can work when you have the stronger length. The other thing that the deep space becomes a problem is as you get farther out, then there's a challenge of pointing your laser that has such a narrow beam, and you have to point ahead. The beam is so narrow that you have to point to where your target is going to be by the time that the light gets there. So the beam is so narrow, for example, that if you're minutes away, then you have to point to where the Earth is going to be, in its relative orbit, where it's going to be at the speed of light when your laser gets there. So that deep space challenge is something that is really unique to the geometry and the physics of it. So that's where DSOC will really be a much better demonstration of that capability. The first part of the question, though, on the applicability to sort of the lunar operations and ops concepts, when we do our support with, particularly with the Illuma-T terminal on the space station, then part of that activity is to demonstrate exchanging data through a relay that to a human spaceflight mission and all that entails, and to do it in a way using networking protocols, DTN, disruption tolerant networking protocols, and interfaces that will directly translate to how we expect the lunar relays to operate over optical links and also through RF links.
Sarah, I need to also add, the LCRD is a technology demonstration. It was not designed to provide any operational support. Now, beyond the demonstration, we may look at applying it here and there to provide some support, in the near-Earth environment. But lunar requirements presently do not require optical trunking, from the moon to Earth. We can meet that with existing RF capabilities, in particular the Ka band. Now, we are looking at these requirements to grow by the end of the 2020, where we see optical communication providing a lot of benefit to support the huge data rate that will be generated at that time. And we are working the technology and as well as the capabilities. And we are hoping that the commercial sector will step in, will provide much of these capabilities. But for now, the LCRD is only there to support the technology demonstration, to give us the experience in communicating from space to space, space to ground, to provide the end user that flexibility. Thank you.
Great. Now we have a question from social media, so I think this one will be for Dave. Jamie Druger on Twitter asks, isn't this what the latest Starlink satellites are doing as well?
So thanks for the question. This is different in that the Starlink has been focusing on using the optical links for the cross links between their spacecraft. So we have that space link component, but we are using the optical link to also get to and from our ground station location. And my understanding of Starlink is that they're still using RF for those links between space and ground, and their optical links are only on the space-to-space link.
Thanks, Dave. All right, for our next question, I will go to Irene in the queue.
Thanks very much. I actually have a quick follow-on to the last question, which is, would the LCRD be able to do a demonstration with Starlink and would there be any reason to do that? What might that show? And I also had a couple questions just generally about the cost of this program and what missions are likely to be first and second in line NASA missions to use optical comms operationally. Thanks.
Great. I will toss to Dave for the first part, and then we'll have Trudy answer the cost questions.
Okay, thanks. Yeah, so our and the Starlink terminals are not compatible to talk to each other. The biggest obstacle would be that the distance between their orbital location and our terminal at GEO would make the link that it wouldn't be strong enough to close the link at that distance. So we are interested in doing demonstrations, like I said, with the guest experimenter program. With anybody that we can work out something where the terminal would be compatible, but somebody would, if it is somebody that's going to put something in low Earth orbit, then they would have to be designing for that path, that path loss, that distance.
All right, and Trudy to answer the cost questions.
And Irene, did you have specific cost questions or?
How much this project is costing?
Sure. So, LCRD's total life cycle cost, and this is what we call the agency's baseline commitment, is $320 million. That's been spent over 9 years. This dates back to 2012. So the cost includes the technology development needed for this, producing the payload, so the hardware, integration and testing, the mission operations, and that includes the Mission Operations Center, the LMOC, that Miriam talked about a few minutes ago. The ancillary things, too, that you need for any project management, systems engineering, and safety and mission assurance costs.
Thanks. And maybe for Badu, the first and second missions that might be in line to use optical comms operationally?
Definitely, and we are looking at the technology as critical for so many missions, in particular to support lunar activities by the end of the 2020s. Also, we are looking at many other missions that will be targeting the Lagrangian points. But we first need to be done with the demonstration of the technology. And the technology then is going to be fully commercialized. Everything that we are doing will be made available to the commercial sector, such that the technology will not only benefit NASA end users, but also other government agencies as well as the private sector. We are hoping this will drive the cost of the payload way down. Definitely, we are looking at the future with a lot of optimism, because the LCRD builds on a previous experiment that we have, which it was the LLCD, where we flew a comm payload around the moon and transmitted 620 megabits per second to Earth, and we had an instantaneous acquisition. So we don't doubt the technology and the capability. All we are trying to do is now with the LCRD is to get the data relaying from space, capability, and having that flexibility for the user to go either to space or to ground. And the potential is so great.
And hey, Irene, I just wanted to follow up, and Badri, just wanted to follow up what you said. There are plans we're currently building, and we'll fly a laser communications terminal on the second Artemis mission aboard the Orion spacecraft, and that's known as the Orion Artemis II Optical Communications System, or O2O is what we call it. So that is planned. So Irene, I just wanted to make sure that we included that in the answer to you.
Thank you.
Yeah, and additionally, we are also looking at the full operational concept for the technology, because really we are looking at the technology delivering huge amount of data to the ground. And overhauling the data on the ground may become an issue. That's why we are working on a low-cost ground terminal that can be provided to the end user, and the end user can have it directly on top of their building, and they can probably buy 3 or 4, distribute them over a wider area network, such that at least one of the terminal will have an open channel without the blockage of cloud. This way, the data can go directly to the end user, reducing the cost of data delivery by a lot. We haven't come up with an estimate, but we expect the data delivery and the cost of overhauling the data to go way down in the future.
Great, thank you. So for our next question, we'll go to Stephen Clark.
Thank you, Stephen Clark from Spaceflight Now. A couple of questions. First, maybe for Dave. Can you remind me of the reason why this experiment was moved off of the commercial host spacecraft and onto STP-SAT-6? Just can you rehash the history of that for a minute, please? And also, maybe for Dave or someone else, if they want to chime in, how does this capability compare to the European Space Data Highway Laser Relay System, which has been operational, I think, for a couple of years now? Just interested in if you can compare what you're doing here with that system, and also would you be looking into doing one of your experiments with one of ESA's Copernicus satellites, since they do have laser comm terminals? Thanks.
Sure, I'd be happy to answer those. So first, the change of the spacecraft. So when we initially went out with the proposal and the procurement of our host spacecraft, we had a certain set of mission requirements, and we had a commercial partner that could meet those requirements. And then we ended up adding additional requirements on our payload that would enable some further experiments, and then we were no longer able to be accommodated on that commercial provider platform. So we had to design up to a certain point, but we weren't able to work with that commercial platform. So then we went back to find another host spacecraft, and that's where the SDP program and SDP-SAT-6 was found to be a match. So for the other part of the question, so with the EDRS or the European data relay, that yes, they've been up operationally. Their operations and is they do, again, it's optical between their orbiting users and the relay, but then they're using the RF to go between the relay and the ground. So that of course gets past all the problems of trying to get your optical link through the atmosphere and through the clouds. And though we have an RF path to get from our payload to the ground, we really want to demonstrate and understand that optical to the Earth link. And a large reason for that is that when you start to do optical links from farther away back to Earth, then for our mission, we have a 1-meter telescope on the ground to support the link. But once you get far enough away, then the size aperture that you would need on the Earth side, we think would become too large, and it will be an ongoing trade, but too large to put an orbiting relay to kind of catch the optical link and then convert it to RF the rest of the way. So in order to really inform that trade, understanding what it takes to deal with the atmosphere and the operational planning and the weather is important to feed into those future designs.
And then, Dave, you may want to also touch on the fact that the frequencies are different frequencies. And,
that's right. And with the compatibility with the current Copernicus, and unfortunately, we're at a different wavelength than what their system operates at, and there's been a lot of work for interoperability, like that's a word that Badri highlighted earlier. So there's been a lot of work happening in our standard organizations to work towards interoperability between agencies and people for for optical links, but the Copernicus links to the EDRS are not interoperable with what we have for LCRD.
And plus, the frequency is not eye safe. While the frequency we selected because we need to go to ground, we selected something that's eye safe, that doesn't cause any issues, and will not be burdened by regulation in terms of eye safety. Although they are changing their frequencies, they are having the dual frequencies on future systems, but the existing system don't have it.
All right, thank you. So for our next question, we will go to George Leopold. And just a reminder, if you have any questions, press *1 on your phone to be added to the queue. Okay, George?
Hi, thanks. Two questions. Aside from the bigger pipeline, the bandwidth issue, I heard someone earlier say faster. Does this technology actually address latency issues, and are those important in terms of deep space exploration? And I just wanted to get some sense as to when is that terminal up at ISS now, and if not, when will it be in place? Thanks.
Yeah, definitely we are bounded by the laws of physics, and we are limited by the speed of light. When we say faster, it has to do in terms of being able to dump large amount of data all at once instead of having to take time to downlink the data to the ground. At this point, we haven't broken any ceiling in the laws of physics. We don't know, probably in the future, but for now we are bounded by the speed of light.
Dave, do you have anything to add or for the second question? About the ISS.
About the ISS. So the ISS terminal is not flying yet. It'll be delivered soon and then put in the into the integration phase, and it's currently scheduled, I believe, sometime in 2022.
Great. I think we have a social. Oh, sorry. Do you have a follow-up?
That's it. Thanks.
Okay. All right. We have a social media question. Brother Timothy Clark on Twitter asks, how will this satellite, due to launch in December, upgrade the NASA space-to-ground system? So I'm going to toss that to Miriam to talk about upgrades to the ground stations.
All right. This is a demonstration of what the overall NASA communications systems could go to. So, don't lose sight of the fact that this is a demonstration, but what we are is a pathfinder to what the next generation of NASA communications can look like.
And if I understand the question, it probably goes beyond just this demonstration. NASA is undergoing a major change where we are commercializing most of our services, and we had put out solicitation from industry for direct-to-Earth support. That's ongoing and will be, most likely commercializing everything by 2023. And as far as data relaying capability, we had from space, we will not be building any new data, tracking and data relaying satellite like the TDRS. We have another program that's also trying to demonstrate the feasibility of commercial providers. All in all, NASA is moving away from routine operation to focus on research and development, for the next generation communication and navigation system. So we would like to commercialize anything that we commercialize and reducing the uniqueness of NASA's requirements to benefit from the, the competitive commercial market and services.
Thank you. All right, I don't think we have any other questions in the queue at the moment, so if you do have some, just a reminder, *1. But I do want to give Avi a chance to talk a little bit about deep space optical communications. So Avi, can you tell us just a bit about where DSOC is now and what are the benefits of demonstrating optical communications in deep space?
Thank you. So the DSOC technology demonstration includes both a flight side development and a ground side development. And for the flight side, the flight laser transceiver is completed. The build has been completed. It's currently integrated to the Psyche spacecraft. The spacecraft itself is undergoing assembly and testing here at JPL. And it's in the highway right now, and it's getting ready for environment testing in the next few months. But as far as DSOC goes, we've delivered the payload. It's bolted onto the spacecraft, and we're waiting to go through the environments testing with the spacecraft. On the ground side, we have two ground stations. One ground station is a transmitter that sends the beacon up to the spacecraft to assist its pointing, and the other ground station receives the downlink from space. The transmitter is located at Table Mountain, California. It uses the NASA JPL 1-meter telescope, and it uses very high-power lasers, which have already been integrated to the telescope and are undergoing live testing and such. And so we will be ready in a few months for the tech demo. The ground receiving station is located at an astronomical observatory down in Palomar, the historical Palomar telescope, the 200-inch or 5-meter telescope. And over there too, our receiver, which will be receiving these very faint photon signals from space, has been integrated to the telescope. And we're in a phase now where we're testing all our receive electronics and detectors by looking at asteroids and stars and tracking them, and that's going quite well. So the ground receiver is almost ready for supporting the tech demo. The launch of DSOC is scheduled in August of 2022. There's, of course, a launch window. And so we're ready and waiting. And the benefits of optical comm from deep space, of course, is to get the higher data rates. For example, you could use higher resolution science instruments to get data back. The human exploration of Mars in the next decade or so would also require much higher data volumes being transferred from those distances back to Earth, as well as from Earth to those distances. And optical can support those. So, for example, one of the capabilities that optical may bring to bear is streaming live imagery, high-definition imagery. So instead of getting these individual frames of rovers or the Mars helicopter, we could probably get a live, live meaning separated by a light time, but still a live stream of high-definition video down from those distances. That's one of the key benefits of going to optical communications. And this can be done using the same kind of resources on the spacecraft that current RF systems use.
Thank you. All right, we do have one last question from social media. This is from a Twitter user for Trudy. Will the astronauts have faster and better communication with Earth?
So the short and sweet answer is yes, ultimately, eventually. And really these capabilities are being developed for multiple uses, and our stakeholder friends in exploration as well as science missions both can benefit from them. So the ultimate answer is yes. Eventually, we'd like you to be looking down at your iPhone and your friend on the surface of Mars texts you pictures and high definition video that are really cool from where they're at. So ultimate goal. The answer is yes.
Great, thank you. All right, so that wraps us up for today. If you want to listen to the recording of this teleconference, that will be available in about an hour. You can dial 866-430-8795 and use the passcode LCRD, and that replay will be available for 30 days. And if you have any follow-up questions or want to request an interview with any of our speakers, you can send me an email at sarah.frazier@nasa.gov. So So that's sarah.frazier@nasa.gov. And finally, right after this wraps up at 2 p.m. Eastern, you can learn more about laser communications and LCRD on NASA TV. We are airing a TV show about laser communications starting at 2 p.m. Eastern. And just for your awareness, there is another NASA payload launching on STPSat-6 alongside LCRD. This is called UVSC Pathfinder. It's the Ultraviolet Spectrocoronagraph Pathfinder, a joint NASA and U.S. Naval Research Laboratory experiment that will study the origins of solar energetic particles, the sun's most dangerous form of radiation. And if you want to learn more about that, you can visit nasa.gov/sunearth or send me an email and I will connect you with the right people. And finally, we hope you will be able to tune in for the launch of LCRD on December 4th. The launch is on a ULA Atlas V rocket, and it will be covered live on NASA TV. The 2-hour window starts at 4:04 a.m. Eastern on that Saturday, so bright and early. Details for the launch broadcast will be available on nasa.gov/live when we get a little bit closer to the launch. So thank you again for joining us. And again, please feel free to email me if you have any questions at all.
That concludes today's conference. You may now disconnect.